Hi, everyone. Hello. Welcome to 2023 Fall Seminar Series. It is a great pleasure to start our very first seminar this semester, having Professor Mark Hersam from Northwestern University, Department of Material Science and Engineering. At Northwestern, Mark is also the director of the Materials Research Center, as well as holds faculty appointments in the departments of chemistry, applied physics, medicine, and electrical engineering. His research focuses on nanomaterials, additive manufacturing, nanoelectronics, scanning probe microscopy, renewable energy, and quantum information science. And his great contribution to research, diverse fields, has been recognized by many awards, just to name a few of them: the Presidential Early Career Award for Scientists and Engineers, TMS Robert Lansing Hardy Award, AVS Peter Mark Award, Emeritus Outstanding Investigator, MacArthur Fellowship, AVS Medard Walsh Award, as well as 8 Teacher of the Year Awards. In addition to research, Mark has also been an elected member of the National Academy of Inventors with over 150 patents, and also has founded 2 companies, NanoIntegris as well as Volexion. These companies focus on supplying materials for battery as well as nanoelectronics. So it's a great pleasure to have you here, Mark. Before I pass the mic to you, I just wanted to remind our audience, if you're in the room, of course, feel free to ask your questions. Raise your hand and ask your questions. We have audience online through Zoom. You can feel free to type your questions through the Q&A option, and we will make sure to ask your question on your behalf. Thank you for coming, and the floor is yours.
All right, thank you very much for the kind introduction and invitation to visit here today. I thank all of you for braving the weather to come here in person, and those of you online, also thank you for taking time out of your busy schedules. So as you can see, today I'm going to talk about area in our research group entitled Mixed Dimensional Heterostructures, which has implications for both electronic and energy technologies. Before I get into mixed dimensional heterostructures, though, let me introduce the constituent of low-dimensional nanoelectronic materials, beginning first with 2-dimensional carbon, also known as graphene. This is a 1-atom thick sheet of sp2 bonded carbon, famous for its high charge carrier mobility. It's also a useful construct conceptually for imagining other low-dimensional forms of carbon, in that if you take this graphene sheet and conceptually imagine cutting out this green shape, rolling it up into a sphere, you get a 0-dimensional form of carbon known as a fullerene. Or if you were to cut out a rectangle from the graphene sheet, roll it up into a cylinder, you get a 1-dimensional carbon nanotube. Or in principle, you can imagine taking graphene and stacking it up into a 3D lattice. And if you did that in an ordered manner, you would get to graphite. In practice, though, you rarely go from graphene to graphite, but rather the other way, starting with graphite and then peeling away down to the atomically thin limit. This process, once you learn how to do it for graphene, can be applied to other van der Waals solids, such as hexagonal boron nitride, which is electrically insulating, molybdenum disulfide, which is a relatively wide bandgap, typically N-type doped semiconductor, phosphorine, which is the phosphorus analog of graphene derived from black phosphorus, narrower bandgap semiconductor, typically P-type doped. And once you've exhausted all of the van der Waals solids, you can imagine taking elements that are not layered in the bulk and growing them directly in the 2D limit, so-called synthetic 2D materials, of which 2D boron or boraphenene is a prototypical example, and that is a metallic material. So we can see, just with this handful of examples, we already have all electronic properties, from metals to insulators and semiconductors in between. And as a result, if we could integrate them into heterostructures, we should be able to realize any and all electronic device phenomena. And that is enabled by the fact that the bonding between these materials is van der Waals bonding. And that has led to a field known as van der Waals heterostructures. This van der Waals heterostructure field is enabled by the fact that van der Waals bonding eliminates the epitaxial lattice matching constraints that exist in conventional covalently bonded compound semiconductor heterostructures. And it's really proliferated throughout the 2D field, including many researchers here at MIT that will layer, for example, graphene on top of hexagonal boron nitride. And we do that as well, but what we argued a few years ago is that this concept of a van der Waals heterostructure is not limited to 2D materials, and that any passivated dangling bond-free surface interacts with another via van der Waals forces, allowing you to generalize this concept to the mixed-dimensional case, where, for example, you could take a 2D material like molybdenum disulfide and layer on top of it a one-dimensional material like carbon nanotubes. And that not only increases the number of permutations for van der Waals heterostructures, but more fundamentally allows you, across an atomically sharp heterointerface, to qualitatively change the nature of the electronic density of states, to qualitatively change the degree of dielectric screening, to imagine excited states such as excitons, where the electron resides on one side of the heterojunction, hole resides on the other side, and as a result, the composite wave function is neither one-dimensional or two-dimensional, but truly mixed-dimensional in character. And of course, that will lead to new physics, new properties, and ultimately new applications. And that's been a unifying theme in our lab, and it's enabled a wide variety of applications, a few of which I'll touch on today, including efforts in next-generation computing, such as neuromorphic or brain-like computing, efforts in taking these materials into solution and using additive manufacturing to enable printed electronics and batteries, to enable the fact that you intrinsically have quantum confinement in the atomically thin limit, to explore phenomena of relevance to quantum information sciences, and then finally the fact that in the low-dimensional limit, there's a high degree of polymorphism, and as a result, you can also make heterostructures where there's no change in the composition of the materials, but all that's going to change is their polymorphic identity. I'll be touching on many of these applications throughout the talk today, but if you're interested in sort of a more overview perspective on any one of them, these review articles listed here would be a good starting point. But today what I want to do is walk you through 3 examples, beginning first with 0D, 2D heterostructures, how we make them, what they're potentially useful for, then moving on to 1D, 2D heterostructures. These are particularly of interest for next-generation electronic applications such as neuromorphic computing, and then concluding with 3D, 2D heterostructures, which are of high relevance to renewable energy and energy storage technologies. That's where we'll conclude the discussion today. But before we get there, let's start with the more fundamental work, beginning with the 0D, 2D heterostructures. And so the question is, what zero-dimensional system are we going to look at? And there are many possibilities. We could look at quantum dots, for example. But in our lab, we generally use organic molecules as the 0D component. And the reason is that organic chemistry allows us to synthetically tailor the properties of the 0D component, for example, the HOMO-LUMO gap. This, of course, is also enabled by the fact that the all-surface nature of 2D materials implies that any chemical modification, such as an organic add layer, will enable exquisite property tuning in its own right due to changes in the local dielectric environment. As I already noted, organic molecules are model 0D components because we have well-defined and tailorable molecular orbital energy levels. And additionally, as is shown by chemists such as Dana Friedman in your chemistry department here, organic molecules provide additional control parameters such as the orientation, spin, and so on to give you further tunability. So let's begin with the simple first example. This is a 0D, 2D heterostructure combining a transition metal dichalcogenide, namely molybdenum disulfide, with a metallocyanine, in this case copper phthalocyanine. If we look at just the simple frontier orbitals, the HOMO-LUMO, compared to the conduction band minimum and valence band maximum of moly disulfide, we see what should be a type 2 heterojunction, and as a result, you should see mutual photoluminescence quenching, which is in fact observed. But additionally, in this mixed-dimensional heterostructure, we have the possibility of a mixed state between the two sides of the heterojunction, wherein you can imagine charge transfer coming from the HOMO of the phthalocyanine to the conduction band minimum of the moly disulfide. And if indeed this state were to form, then we should see a new peak at lower energy or longer wavelength in the optical absorption spectrum, which indeed is clearly observable as you see here. If we look at MOS2 or copper phthalocyanine alone, we do not see this peak out here at 720 nanometers or so, but it's evidently present in the mixed-dimensional heterojunction. Now, as I alluded to, the beauty of organic chemistry is that we can now look at a whole series of such heterojunctions just by changing the metal center and the metallo-phthalocyanine. For example, looking at the series cobalt, nickel, copper, and zinc. And I'm not going to walk you through all of these spectra in great detail, but just by eyeballing them, you're going to see that there are clear differences in the nature and wavelength of the charge transfer state, and this can be explained by differences in the frontier molecular orbital energetic location with respect to the band structure of the 2D molybdenum disulfide. Additionally, you can look at other effects, such as Raman spectroscopy. One thing that you observe in Raman spectroscopy is that the degree of Raman enhancement of the molecular vibrational modes depends upon the dimensionality of the underlying substrate. If I were to put a metallo-phthalocyanine on bulk MOS2, I can barely see the vibrational modes of the metallo-phthalocyanine. However, when I thin down to the monolayer limit, we see significant Raman enhancement, and the peaks become evident. Now, interestingly, as you look at this Raman enhancement as a function of the metallo-phthalocyanines metal atom identity, you see a very clear trend, which appears to depend upon the metal d orbital. I will note that the d orbitals are not the frontier molecular orbitals, so this is not just explained by the HOMO-LUMO gap, but instead, if you look carefully at the d orbitals, which are the non-frontier orbitals, you see a correlation between their energetic position and the degree of Raman enhancement. The point of this slide is to note that it's not just HOMO-LUMO that matter in the zero-dimensional side of the mixed-dimensional heterojunction, but also the non-frontier orbitals, giving you further tunability over the possible properties that could be realized. Next example I want to give is C70 indium monoselenide. This is a system that I'm introducing because we've changed the orientation energetically of the 2D and 0D component. In this case, we would anticipate electron transfer from the 2D side to the 0D side, whereas in the phthalocyanine MOS2 case, it was the inverse charge transfer. These are formed by evaporating C70 onto indium monoselenide in ultra-high vacuum. The reason we do this in ultra-high vacuum is that indium monoselenide is highly reactive chemically. Another advantage of doing this in ultra-high vacuum is that you can then probe, using scanning tunneling spectroscopy, what indeed the energy level locations are. And we see that the scanning tunneling spectroscopy confirms the simple band picture that is shown schematically here. What we then do is we take that system, we shine light on it, we measure with scanning tunneling spectroscopy any shifts that occur in the electronic density of states. And what you observe is a very obvious shifting. This is the peak affiliated with the lowest unoccupied molecular orbital of C70, which you would typically think should not vary as a function of optical irradiation. And yet we see very clearly in scanning tunneling spectroscopy a shift on the order of 250 millivolts, which is quite significant and well above KT at room temperature. To confirm that this is indeed a real effect, we performed additional characterization, in this case Kelvin probe microscopy. Kelvin probe microscopy also very clearly shows shifting in the energy level. The measured value here is 230 millivolts, in close agreement to the 250 millivolts we observed with scanning tunneling spectroscopy. So this does appear to be a real effect. Why does it occur? So to look at this, we collaborated with Pierre Derancey at Argonne National Laboratory, who performed density functional theory calculations. The first thing that we would anticipate upon photoexcitation is that we should have electron transfer occurring from indium selenide to C70, and concurrently Hall transfer occurring from C70 to indium monoselenide. When that occurs, you'd anticipate there to be a dipole that is set up right at the heterointerface. Because this is a low-dimensional, mixed-dimensional heterojunction, we have weak dielectric screening, and as a result, the presence of a dipole will introduce energy level shifts of the corresponding molecular orbitals. And that resulting dipole quantitatively leads to shifting on the order of 2 to 300 millivolts, consistent with the scanning tunneling spectroscopy and Kelvin probe force microscopy. The key point here is that screening, or lack thereof, is of utmost importance in these low-dimensional heterostructures, and we're going to be exploiting that later on in the talk. For now, though, I'll only move on and give you another example of where a 0D, 2D mixed-dimensional heterostructure adds value compared to just the 2D system alone. For this, what I want to talk about is not the room temperature behavior, which I already described, but to observe what happens when we go to low temperatures. And in particular, if you take moly disulfide and you look at, for example, photoluminescence at room temperature, you'll see one clear peak, which you can attribute to excitonic effects in the moly disulfide. However, when you go to low temperature, what you observe is that there's a secondary peak that emerges. This is often referred to as a defect emission peak. This peak is quite problematic in many contexts, including in quantum information sciences, because these defect peaks will complicate the interpretation of single photon emission spectra from transition metal dichalcogenides. So the question is, can we do something about this defect emission? And as you can see, when we deposit a 0D component on top, in this case cobalt phthalocyanine, we see very strong quenching, particularly of the defect emission. So this is a manner in which we can utilize a simple organic add layer to clean up the spectrum and enable you to use this material in a variety of applications, including quantum information sciences. Now, if you look at this as a function of the phthalocyanine metal center, again, you see a clear trend occurring here, where the degree of quenching of the defect peaks will depend upon the metal center that's present in your phthalocyanine. I note that in these experiments, we utilize chemical vapor deposited moly disulfide. This material is relatively defect laden, and as a result, the defect peak is actually the dominant peak. This small peak over here is the exciton peak. These are simply coming from the defects present in the material, and therefore it's much easier to observe the effect of the metal center in the phthalocyanine in terms of quenching of that defect peak. In any event, a question then arises, why does this depend upon the metal center in the phthalocyanine? So again, we turn to Pierre Derancey at Argonne National Laboratory. He looked at what charge state should be preferred for the most common defect in moly disulfide, namely sulfur vacancies. He found that the negative charge state, which is the dark state, in other words, the state that does not emit light, is favored in the observed order ranging from cobalt to metal-free phthalocyanine in the same order that's observed experimentally. So this is a case where the interaction between the 0D component and the 2D component of the mixed-dimensional heterojunction is influencing the charge state of the point defects in the 2D system, thereby allowing you to quench the undesirable contributions of those defects. Okay, so I suggest that this might be useful in the realm of quantum information sciences. And if you look in the world of single photon emitters, the most popular 2D material is tungsten diselenide. Tungsten diselenide, if it's appropriately strained and has appropriate defects, will show single photon emission. The question is, what if you form a mixed-dimensional heterojunction between tungsten diselenide and some organic species? And in this case, the organic species we're looking at are nitrophenyl oligomers. These are oligomers that are formed from the polymerization of nitrobenzene diazonium, which is a famous chemistry for functionalizing carbon nanotubes in graphene. At room temperature, the effect is pretty similar to what I showed you for the phthalocyanines. You get mutual photoluminescence quenching and therefore a reduction in the photoluminescence at room temperature. More interestingly, though, is when you go to low temperature. So when you go to low temperature and you look at tungsten diselenide, the photoluminescence spectrum becomes somewhat more complicated. There's a number of excitonic and trionic features in addition to defect states that we talked about before. And when you add the organo functionalization layer, what you observe is quenching of those defect peaks. What's interesting for the case of quantum information sciences, though, is the fact that if you have strain additionally present in your tungsten diselenide, which in this case is occurring from randomly occurring wrinkles that are present in the film, but these also can be induced by intentionally introducing strain, for example, via a nanopillar substrate, then what you observe is the defect spectrum becoming much more complicated, some very sharp peaks emerging. These are the single photon emitting peaks. And this is why people are interested in this material for quantum information applications. The problem, though, is that this defect emission is very complicated. There's many overlapping peaks. The single photon purity is quite low. And as a result, the question is there a way to clean up this spectrum? And what you observe is that when you put down the organic add layer, is that these peaks are largely quenched. And instead, what you see emerging is a single, very sharp single photon emitting peak. This peak, if you then perform so-called G2 measurements, shows very clear indication for single photon emission. So the point here is that the mixed dimensional heterojunction cleans up the single photon emission spectrum, giving you high single photon purity. Why is this the case? Well, the reason is that the interaction between the nitrophenyl oligomer and the tungsten diselenide results in the establishment of new states in the band gap region. These new states are near the conduction band minimum. And if you have a distribution of molecular orientations and oligomeric identities, then what you will achieve is a band of states that are coming from the zero-dimensional side of your heterojunction that reside just below the band edge of your tungsten diselenide. The net effect is that the emission from all of these states near the band edge become quenched, or at least become dark. And as a result, the only energy that remains is the lowest energy peak, which then shows strong single photon emission. So this is a case where we're now utilizing, again, the organic add layer as a means of passivating, or at least turning off the effect of the defect states, thereby giving you much more homogeneous and reliable single photon emission. OK, let me move on to the next topic, which is to look at how we can utilize 1D, 2D mixed dimensional heterojunctions, in this case to achieve asymmetric dielectric screening, which you will see is of interest to next generation computing, in particular neuromorphic electronics. So since many of you may not think about neuromorphic computing every day, let me give you a quick introduction. The reason people care about this is that, as we all know, the current world in which we live is one where there's huge data. There's great interest in artificial intelligence for exploiting such big data. The problem, though, with big data and artificial intelligence is that it leads to uncomfortably high power consumption for conventional computing, to the point where training of AI algorithms is consuming now a significant fraction of the total grid's energy. This is simply unsustainable path moving forward, and as a result, we need to come up with new hardware that's much more energy efficient. And in particular, the reason this is high power is that a conventional computer has a von Neumann architecture where we have information processing at one point, memory at another, and we need to move the data back and forth. And the more data you have, the more data you need to move, and the more power consumption you have. In contrast, if we were to look at the brain, how the brain does computation is to co-locate memory and information processing. And this is why the brain is orders of magnitude more efficient than we have for conventional digital computing. And that's the underlying motivation of neuromorphic computing. Because conventional transistors can't do neuromorphic computing in an efficient manner, there's high interest in looking at other types of devices. The most popular one is a memristor. This is a resistor that remembers its voltage history. It's intrinsically a memory element, a non-volatile memory element, and therefore it's quite good for memory. Also reasonably good at pattern recognition, but not particularly good at information processing or higher order cognitive function. Moreover, memristors are typically two-terminal devices, whereas if we look in a biological neural network, we have hundreds, if not thousands, of interconnections between neurons. And as a result, memristors fail to achieve that hyper-interconnectivity that is achieved in the brain. And as a result, in our lab, we've really been trying to rethink neuromorphic devices. If we're really attempting to mimic a biological neuronal network, then we'd like to meet the following criteria for our solid-state electronic device. First, we'd like to be able to achieve highly nonlinear voltage spiking, analogous to the action potentials in biological neurons. We'd like to be able to perform memory and information processing function at the same point in space. In other words, can we combine a memristor and a transistor into one device? And can we do this in a manner with multiple terminals to enable high interconnectivity and reconfigurability? And so you can probably guess how we do it. We exploit mixed dimensional heterojunctions. And in particular, the first one I want to introduce is a 2D, 1D mixed dimensional heterojunction between 2D molybdenum disulfide, which is N-type semiconductor, and 1D carbon nanotubes, which are P-type semiconductors. So this is a PN heterojunction, and it will show a rectifying current voltage curve like a traditional PN junction diode. But what's different about this PN junction diode is that the materials are atomically thin. As a result, they are easily gated due to weak dielectric screening. Moreover, because it's a mixed dimensional heterojunction, the screening is weaker on the 1D side than the 2D side, giving you an asymmetry in the gating in a dual gated geometry. The net effect of which is that you can achieve exquisite tunability over the resulting current voltage response. Particularly, what you observe, if you look at the current through the device as a function of one of the gate voltages, in this case the top gate, is that the device is off at high negative voltage because you fully depleted the N side of the junction. It's off at high positive voltage, you fully depleted the P side of the junction. Only at low gate voltage is the device on. And as a result, you get this Gaussian response, also referred to as an anti-ambipolar response, because it's a flipped over version of an ambipolar transfer curve. The beauty of this device, though, is due to the asymmetric screening and the fact that we have two gates, that we can fully tune the Gaussian response. We can tune the peak height, the peak position, the peak width at will. And the reason this is of interest is that when you have a Gaussian output characteristic which is fully tunable, you can now realize highly nonlinear voltage spiking responses in relatively simple circuits. And that's indicated here. I take one of those mixed dimensional van der Waals heterojunctions. I combine it with some simple circuit elements like resistors and capacitors. And if I input a synaptic current into the circuit, the resulting voltage as a function of time is a spiking response, where the details of that spiking response faithfully mimics that of an action potential in a biological neuron. What's interesting, though, about this artificial neuron compared to a traditional biological neuron is that we can tune the details of the spiking response just by changing the voltages applied to the device. So it's a highly reconfigurable artificial neuron. To illustrate that, what I'm going to show you is a few examples where all we're doing is tuning the peak position of the Gaussian response. Depending upon where the operating voltage is compared to the peak of the Gaussian, you'll either see single spiking behavior or multiple spiking behavior where the time scale or spacing in time between spikes is tuned based upon how far you move down on the positive transconductance side of your anti-ambipolar response, a high degree of tunability and reconfigurability. You can go one step farther. This is work that's just about to be published, where now what we're going to do is intentionally vary the nanotube density. That will allow us to more exquisitely tune the asymmetry and the dielectric screening across the mixed dimensional heterojunction. That allows you to not only get exquisite tunability over the Gaussian response, but also achieve a sigmoidal response or a linear combination of the two. This is also of high interest for machine learning. In machine learning, one of the first classification algorithms you learn in undergraduate machine learning is the so-called support vector machine. And when you look at support vector machines, the gold standard is not to do a single Gaussian or sigmoidal kernel, but rather to mix the two together. We can now do that mixed Gaussian sigmoidal kernel in hardware using a single device. If you attempt to do the same machine learning hardware equivalent in CMOS, it requires 100-fold more devices, which is why it's typically not done. It's just too cumbersome. But with a single device, it can be done in a highly efficient manner. We applied this to a particular use case, in particular doing classification of electrocardiogram data, where in particular what we were attempting to identify was arrhythmia in the patient. By personalizing the mixed kernel, which we can do just by changing the voltages applied to our device, we can push the accuracy for arrhythmia detection close to 100%. again in a manner where you have 100-fold fewer devices than CMOS. This makes it considerably more energy efficient, allows you to do the machine learning processing on site, for example, in the wearable device, as opposed to transmitting all the data to the cloud, which of course comes with a lot of wasted energy consumption. So edge computing is sort of enabled by this type of device. Okay, so that's the neuron side of a neuromorphic circuit. But if you look in a biological neuromorphic context, not only do you need the neurons, but the connections between the neurons, the so-called synapses. The synapses are going to be strengthened or weakened in their connectivity as you learn or forget. So the question is, can we have a device which is going to increase in its conductance or decrease in its conductance as a function of the number of times that it sees a particular input signal? The traditional way of doing this is with a memristor. I mentioned memristors before. These are resistors that remember their voltage history. They're like the synaptic connections in the brain, in that the more voltage pulses you send in, the higher the conductance state, or if you flip the polarity of those voltages, you'll decrease the conductance, equivalent to forgetting that state. So the question is, can we achieve memristive phenomena in a mixed-dimensional heterojunction? The way we do this is an interesting case. It's polycrystalline MOS2. Polycrystalline MOS2 is mixed-dimensional in the sense that it's a 2D material, but the grain boundaries that are present in the polycrystalline material are one-dimensional in nature. And what we observe when we look at current voltage curves in polycrystalline MOS2 is that initially the device will start in a high resistance or low current state, but at some critical voltage it will switch into a low resistance or high current state, and it will stay in that state until you go to the opposite bias polarity. This two-terminal strong hysteretic loop is the characteristic behavior of a memristor. It turns out, if you look at this in detail, the reason this occurs is that defects in the MOS2, such as sulfur vacancies, are being driven by the lateral field. Those sulfur vacancies are also dopants in the material, and if you reconfigure the doping profile in the channel, you'll reconfigure the resulting current voltage curve. Those defects have their motion mediated by the grain boundaries, and that's why it's necessary to have polycrystalline MOS2 to achieve the strongest memristive response. Okay, so what? Well, memristors are not new. They've been around for at least a decade or so. So why would I want to do this in MOS2? Well, the reason is that molybdenum sulfide is low-dimensional, and as a result, you can gate the response, which means that you can now utilize the gate potential to tune the details of your memristive response. And depending upon the geometry of the grain boundaries with respect to the channel, you can either use the gate to tune the trip voltage between the high and low resistance states, or to tune the overall conductance of the device, in this case, tuning it by many orders of magnitude. And in particular, this gate tunability of the overall current level is a transistor-like response, while from the source drain voltage perspective, we still have a memristive loop. And as a result, this is a device that combines a memristor and a transistor into one device. We call it a MEM transistor for short. It is the ultimate scaling limit of putting information processing and memory at the same point in space, and as a result, presents tremendous opportunity in neuromorphic computing. Now the problem is, in this early work, is that when we had a small number of grain boundaries per device, is that there'd be great variability from device to device because it would depend upon the geometry of the grain boundary with respect to the channel. However, we're able to get around that issue by going to even smaller grain size, MOS2, which implies that at the device level, we have many different grain boundaries present. And as a result, you get an averaging over the stochastically distributed grain boundaries at the single device level. This substantially improves device yield and homogeneity from device to device in the array. In these highly polycrystalline MOS2 devices, this is the characteristic current voltage response. We still see a strong two-terminal hysteretic loop. You will note that the degree of hysteresis is lower at negative bias than positive bias. The reason for this is that in these devices, all the action is happening at the Schottky contact, which give you a rectifying response, and as a result, a difference in positive versus negative bias polarity. Additionally, if we look at a series of those two-terminal IV curves at different gate voltages, we see dramatic tunability in this case by another 6 orders of magnitude, so we have a strong transistor-like response. There's also some subtleties here, which we can talk about later if you're interested, such as the size of the hysteretic loop is further tuned as a function of the gate voltage. Additionally, what these MEM transistors allow you to do is to begin exploring the limit of higher order interconnectivity. The reason is that this is a planar device, and as a result, you're not limited to 2 contacts. You can put more contacts into the channel region. In this case, we have 6 contacts to the channel. If indeed the mechanism is that laterally applied fields are driving defect motion and therefore reconfiguring the doping profile on the channel, that should not only influence the current flow in that direction, but also in the orthogonal direction, for example, between contacts 2 and 4. This is indeed the case. What I'm plotting here is the current voltage response between contacts 2 and 4 as a function of voltage pulses between contacts 5 and 6. And you see very clear non-volatile tuning of the orthogonal conductivity as a function of voltage pulses. This is a so-called heterosynaptic response. Heterosynaptic responses are well known in neuroscience, not previously demonstrated in solid-state electronics, and so the multi-terminal MEM transistor allows us to more faithfully replicate the behavior of biological neuronal networks. In addition, because this is an atomically thin device, there's nothing stopping you from gating from both sides to make a dual-gated MEM transistor. This has a couple of distinct advantages. One is that you can now integrate MEM transistors into a so-called crossbar array. This is a traditional architecture for memristive neuromorphic circuits. One of the problems with a memristive neuromorphic crossbar array is that you have crosstalk between the elements in the array unless you introduce another circuit element like a transistor to uniquely identify and address one and only one point in the array. Whereas with a dual-gated MEM transistor, you have that second tuning parameter there for free. You can use one gate to identify the point that you're addressing in the array and then still have the MEM transistor performance from the other gate. Additionally, when you have 2 gates, you now have further tunability over the synaptic response, which can be useful in a variety of classification algorithms. Additionally, I want to stress that this behavior depends very much so not only on the grain size of your material, but also the defect density that's present in your material. So for example, if I take a MEM transistor made from chemical vapor deposited MOS2, and I grow it on sapphire compared to growing it on silicon dioxide, on sapphire, you get a much lower defect density. That will imply or should imply that your memristive response is attenuated, and that's indeed the case. We see smaller memristive loops here. Or equivalently, what you're doing is increasing the influence of the gate voltage in this device. So the transistor response or the gate control will be enhanced if you reduce the defect density in your polycrystalline MOS2. This is indeed the case. In fact, you get so much tunability over the synaptic response that you can tune with single input bias polarity from a potentiation or increasing in conductance behavior to a depression or reduction in conductance behavior for the same voltage polarity. This is exactly what happens in neuroscience. It does not happen in traditional memristive neuromorphic circuits where you have to change the bias polarity. This is, again, more faithfully imitating what happens in biological systems. The net effect is that if you're better at mimicking a biological system, you should be able to do higher level cognitive function than has been previously demonstrated in solid-state electronics. One of those is something called unsupervised continuous learning, which we've now implemented in spiking neural networks. The beauty of unsupervised continuous learning is that you can train your neural network to do multiple tasks without completely forgetting the previous tasks that you trained it. Very similar to us in real biology, where when you learn something new, you don't need to forget everything else that you previously knew. But you often have to reallocate some of your resources to the new task, and as a result, you lose something, but not everything. And as a result, if you want to relearn that second task, it's much quicker the second time around. This is something that we can now implement in solid-state electronics, and the net effect is that you circumvent traditional trade-offs between For example, image recognition, accuracy, and resource allocation. This is where we're going in our lab to, again, very faithfully mimic biological systems to go to higher and higher order cognitive function. OK, in the last 10 minutes or so, let me now move on to the final case, and that is the 3D, 2D mixed dimensional heterostructure. And in this portion of the talk, the application that we'll be talking about are batteries. So a quick primer on lithium-ion batteries. If you look at a lithium-ion battery, you have two electrodes, an anode and a cathode. You have an electrolyte between them, and typically a separator that prevents the two sides of the battery from shorting to one another. And depending upon if you're charging or discharging, you'll move lithium ions back and forth between the anode and the cathode. And the question that we asked in our lab is there any opportunity for nanomaterials in batteries, or more to the point, mixed dimensional heterostructures? And what caught our eye was not the anode or the cathode, but rather these two layers here labeled SEI. These are the solid electrolyte interfaces. These are layers that build up at the surface of your electrodes during electrochemical cycling. They are generally deemed to be problematic because it leads to a reduction in capacity as a function of cycle time and will ultimately limit the lifetime of your battery. So our thinking was what we should do is replace this structure with a mixed dimensional heterojunction, where we're still going to use a 3D bulk material for the cathode, but put an artificial SEI made from a two-dimensional material on the surface. And that way we will control and hopefully improve the cycling performance of the lithium-ion battery. OK, so how do we do it? Well, what we're going to do is take our cathode particles, in this case lithium manganese oxide. We're going to put them into solution with solution process graphene. We process this with a polymer called ethyl cellulose, forming a stable dispersion. We then cast that onto a substrate. And if we have enough graphene present, we're going to find that that graphene will form a coating on top of the cathode particles that make up your composite electrode, giving you a conformal few-layered graphene coating. This will serve as the artificial SEI layer. It presents a physical barrier between the electrode and the electrolyte. It should mitigate unwanted chemistry between the two. In the case of lithium manganese oxide, that unwanted chemistry is manganese dissolution. And when manganese dissolves out of your cathode, you, of course, get a loss in capacity on the cathode side. But additionally, that manganese will find its way over to the anode, where it also causes problems on the anode side. So in a full cell battery where you use graphite as your anode, you see a very dramatic reduction in capacity upon cycling for lithium manganese oxide. This is why lithium manganese oxide is generally not used in commercial settings. In contrast with the graphene-coated case, as you can see here, particularly in the full cell data on the right, is that you get much more stable cycling performance. And when you analyze how much manganese has been lost in the cathode or how much manganese has found it to the anode, you find that it is mitigated in both cases. And as a result, you've achieved that reduction in unwanted chemistry between the electrolyte and the electrode. Additionally, I'll point out that graphene is highly conductive material. That means that a graphene encapsulation lowers the impedance of your battery, which allows you to increase the kinetics of the battery. In other words, you can go to higher cycling rate performance. That's shown here, where we're showing cycling at different cycling rates. 1C means we're cycling in an hour. 20C means we're cycling in 3 minutes. Pink is the control, where we see dramatic reduction in capacity at high cycling rate, whereas for the graphene encapsulated case, you maintain much of your capacity even at 20C rate, which is, of course, of high interest for many applications, including electric vehicles. The issue, though, is that the way in which we did this initially is that we were just mixing together graphene and the cathode particle. And as a result, to make sure you got coating on the surface of every single cathode particle, you had to put in a lot of extra graphene. That is, of course, not great, because graphene is just dead weight in the battery. And obviously, you'd want to minimize the amount of dead weight that's present. And as a result, we had to come up with a much more efficient way of getting the conformal coating on the surface of the cathode particles. This was achieved by utilizing a trick from soft matter, in particular the use of Pickering emulsions. For those of you who don't know about Pickering emulsions, how they work is you take two immiscible solvents, in this case acetonitrile and hexane, If you shake them up, you'll form an emulsion where you have small droplets of hexane in the acetonitrile. But if I just let it sit, it will eventually phase separate like oil and water. However, if I have a third party present, in this case our graphene, the graphene will be recruited to the surface of the hexane droplets. It will stabilize the interface between the two immiscible solvents, giving you a stable emulsion. So a Pickering emulsion is one where a third party, in this case graphene, stabilizes the emulsion. So what? Well, it turns out that the particles we're trying to coat, namely the lithium metal oxide particles, disperse selectively in hexane compared to acetonitrile. And as a result, if I add the particles to that emulsion, they will be recruited to the interior of the droplets. By tuning the emulsion size to be just bigger than the particles, which can be done by the ratio of the two solvents, you can now have a situation where you have one and only one particle inside of each droplet. And remember, on the surface of the droplet, you have the graphene that you want to use to coat the particle. The final trick is to exploit fractional distillation, namely the fact that hexane has a lower boiling point than acetonitrile. And as a result, upon heating, the inner solvent evaporates first, causing the particle size to decrease and the graphene to collapse around the surface of your particle, giving you a beautiful coating at an order of magnitude less graphene than you had in the previous random mixing approach. This, therefore, allows you to achieve a very high volumetric and specific capacity for your total electrode, since you've minimized the dead weight or excess carbon, approaching theoretical limits. This is done using all solution-based processing, therefore compatible with scalable manufacturing. This is the basis of our new company, Valexion, which is bringing this technology to many electric vehicle manufacturers. For completeness, I will note that this approach is one that works not only on conventional cathode materials like lithium, nickel, manganese, cobalt oxide, but can also enable next generation cathode materials such as lithium nickel oxide. Lithium nickel oxide has not made it commercially yet because it has an issue. In particular, at high states of charge, the oxygen becomes unstable and is liberated from the cathode. This is so-called oxygen evolution. You can see this very clearly in mass spec. At high states of charge, you see oxygen coming out of your electrode. This leads to a cascade of problems, ultimately leading to a short lifetime of the battery. In contrast with the conformal graphene coating, you get essentially a hermetic seal on the surface. It creates a large barrier for oxygen evolution. You no longer see it removed at high states of charge, and correspondingly, you get a much higher cycle life. I will note for completeness that this also is applicable to the anode side of the battery. If you have an oxide-based anode like lithium titanium silicon oxide, you can again get the beautiful graphene conformal coating. In this case, it enhances the conductivity and therefore the rate performance on the anode side of the battery. The point is that this coating works well on both the anode and the cathode side, which then leaves one final part of the battery left, and that is the electrolyte. So to conclude, let me talk about the most recent work we've been doing on trying to address the electrolyte in the lithium-ion battery. And in particular, what we'd like to do is replace the conventional liquid electrolytes that are used in lithium-ion batteries with a solid electrolyte. Now, this is for many reasons, including the fact that it should be considerably more safe because the flammable solvents in your liquid electrolyte is what leads to the flammability hazard and ultimately explosion hazard for lithium-ion batteries. This is quite problematic, particularly in electric vehicles. So the way in which we're going to overcome that is to utilize another 2D material, in this case hexagonal boron nitride. We're going to blend it with ionic liquids to form a gel. The beauty of the hexagonal boron nitride is that it's electrically insulating, has exceptionally high thermal and chemical stability, and as you'll see in the next slide, allows us to get a much improved mechanical properties compared to conventional ionogel electrolytes. The reason for this is twofold. One is that exfoliated HBN has high surface area, giving you more interaction with the ionic liquid. Additionally, we put an amorphous carbon coating on the hexagonal boron nitride that drives further interactions with the ionic liquid, giving us strong gelation and therefore high storage modulus without compromising ionic conductivity. This is useful for suppressing lithium dendrite growth in a solid-state battery. Additionally, that strong interaction between the HBN and the ionic liquid implies that you get very high stability, particularly at high potentials. In this case, what I'm comparing is the ionic liquid alone compared to the HBN ionogel. And you can see at high charging voltages up to 5 volts, you get considerably higher stability than the liquid alone. You can then use this HBN ionogel to make a full solid state battery. The charging and discharging performance is highly stable with very slow capacity fade. Also, interestingly, these HBN ionogels, due to their high thermal stability, allow you to operate your battery at high temperatures up to 175 degrees Celsius. If you were to take a conventional lithium-ion battery and put it on a hot plate at about 60 degrees C, it would go up in flames due to the flammable solvents that are used for the liquid electrolyte. These batteries are perfectly rock-solid stable to at least 175 degrees. In fact, at this temperature, what's degrading is not the electrolyte, but the electrodes themselves. So that all looks good, but there's a catch. And the catch is that if you look at the full electrochemical stability window of the ionic liquids that we're using, you see that it goes down to only 1 volt. You can go up to 5, as I showed you before, but only down to 1 volt. So the delta V is only 4 volts. That does not allow you to use conventional anode like graphite on the anode side of the battery. So you may think to yourself, well, why don't you just change your ionic liquid? And you can do that. And if you change your ionic liquid, you can reach the low potentials of graphite, but then you compromise the high potential range. So the delta V is still only 4 volts. This is why ionic liquids never made it in lithium-ion battery commercial setting. The difference, though, with an HBN ionogel compared to an ionic liquid alone is that it's a solid. And as a result, we can now make a layered heterostructure where I put the high potential ionogel on the cathode side, the low potential ionogel on the anode side, and in that way we can achieve the full stability window from 0 to 5 volts. This indeed works quite nicely. In the heterolayered case, we see exceptionally high cycling stability, whereas if I were to just blend the two ionic liquids together, they would both touch both of the electrodes. They would both undergo a degradation upon cycling, and as a result, you see in that case in black, very fast capacity fade. So this looks quite promising. I would say probably almost ready to go commercial, but there's one final problem, and that is the way in which we made these ionogels initially was to take hexagonal boron nitride ionic liquid, put it into a mortar and pestle and just grind it, and then slap it onto the electrode, compress it in a coin cell, which is good enough to publish a paper maybe, but I would say not a scalable manufacturing strategy. And so most recently, what we figured out how to do is to achieve this same structure utilizing a traditional additive manufacturing, namely blade coating. It's pretty simple fix. What you do is add a polar diluent solvent, namely DMF, that allows you to form an HBN ionogel slurry, which upon evaporation of the solvent leads to the strong gelation that I showed you before. This allows you to blade coat whatever electrode you like, including pure lithium. Because it goes down as a viscous slurry, it will conform to rough surfaces, which gives you good conformal contact. Upon evaporation of the solvent, you get strong gelation, therefore you get strong lithium dendrite. Growth suppression, allowing you to go to high current densities with high cycle life. All right, with that, I think I'm out of time, so let me quickly conclude. I tried to make 3 points today. The first is that the synthetic tunability of organic molecules provides control over photonic 0D, 2D heterostructures. Secondly, for 1D, 2D heterostructures, the opportunity is to exploit asymmetric electrostatic gating to achieve highly nonlinear neuromorphic responses. And finally, in the 2D, 3D heterostructure realm, we're using the 2D material as a coating or a stabilizing agent, which improves stability for energy storage technologies. With that, let me conclude by acknowledging my research group, all the funding agencies in my lab, and thank all of you for your kind attention.
Thank you for a wonderful talk. We have time for a couple of questions, but before we get to the questions, just a reminder, there is going to be a reception next door, so you'll have more time to be able to meet Mark and also ask you questions.
Thank you very much. With regard to the MEM transistor, there are many applications for that, but the simplest one would seem just to be more energy efficient computation. How far in the future do you think that utilizing that technology for reducing memory power consumption would be?
Yeah, I agree with you. And there's several challenges that need to be overcome. One is sort of integration into scalable architecture. So the crossbar array is the simplest case. The dual-gated MEM transistor looks to be quite promising in that context. I think there's still work to be done in engineering the materials themselves to have sufficiently high homogeneity and reproducibility from device to device. It's much better than when we started. I would say probably not good enough to go commercial. And as a result, there's high interest in improving the controllability of the growth. One member of your faculty, Jing Kong, works a lot on growth of 2D materials. I think work of her, us, and other labs are making progress in that direction. But I think we're to the point where we're now making many device arrays, and we can begin to explore exactly what you're suggesting.
Thank you for the very nice talk. You showed these very nice TM images of graphene coating your electrodes. Question one, I guess, is it truly coating all of the particle? And then what implications does that have for lithium diffusion through this dense layer?
Great. Yeah. So am I cherry picking a really nice region? That's a fair question. I would be suspicious too. There's a couple of tricks that give this a very low pinhole density. One is that the size of the graphene sheets is small compared to the surface area of the particle that we're coating. That's actually quite important. If the area of the graphene sheet were similar to the surface area of the particle, then the only way I could get a conformal coating is by wrinkling or crumpling, which would give me gaps. Because our graphene is small compared to the surface area, it goes down flat. So it's like we're tiling or forming a patchwork quilt around the particle, which then begs the question, what about the seams in your quilt? Well, one of the subtle details here is that we use a stabilizing polymer called ethyl cellulose, which will give us a secondary polymer coating around the graphene sheets. Now that polymer is not conductive, but what we do is we thermally heat it to about 250 C. That largely volatilizes the ethyl cellulose. Most of it leaves, but a small amount of amorphous carbon remains. That amorphous carbon is templated by the graphene to give you high sp2 content. So you get a secondary sp2-rich coating around the graphene. That fills in the seams, but it fills in the seams with something that's not perfect. Because if it was perfect graphene, you're right, you'd have a big lithium diffusion barrier. Imperfect graphene, lithium goes through pretty easily. So yeah, it's all of those things put together, which gives you something that's essentially pinhole free, creates a barrier between the electrolyte and the electrode, but still allows lithium to go in and out.
Any other questions?
Is there a question here?
Hi, yeah, thanks very much for the nice talk. So I had a question on how you choose your materials systems, because already with like 2D, there's kind of infinite combinations.
Yes.
And then when you bring it to all the other combinations, there's so many. So say, for example, with the C70 and indium selenide, how did you converge on, okay, that was the two materials we were going to put together?
Yeah, so it really depends on what you're trying to do. In that case, we had done the phthalocyanine MOS2, and the type 2 heterojunction had one orientation, so we wanted to flip it. So indium selenide C70 gave us the flipped type 2 heterojunctions. We could look at the electron and hole transfer in the opposite direction. That was the motivation there. But you're right, there's endless, almost endless possibilities. That's hopefully going to keep us busy for a while. But it's a challenge in how do you choose? Like, how do you prioritize what to go after? And often it's driven by some desire to achieve a new phenomenon or a targeted application. That will be one of the constraints that we'll consider. But yeah, I think it's a fair question to ask. Is there a way to systematically screen that phase space efficiently? We would perhaps look to some of our theoretical colleagues for help in that regard, in that computationally you can screen much more quickly than experimentally. So I think that's likely where we will go in the future.
Thanks.
One last question. Okay, so if not, let's thank Professor Hersam for a wonderful talk again.
Thank you.
So there will be a reception next door, so please join us for the reception and you'll have more time to talk to Professor Hersam.